Okay. Next, what I want to do is I want to talk about what's called the adjoint matrix. And there's actually two different notions of what it means to be an adjoint matrix. So this is sometimes called the classical adjoint matrix. Okay. Um, so the classical adjoint matrix, what it is let's do this with an example. Let's say we have the matrix A, which is going to be 1, 3, 2, 0, 1, 4, 1, 3, 1. Okay, not really being very careful with my values that I picked here. We can even make some of them negative if we want. Let's say negative 1, negative 3, 2, 0, 1, 4 is 1, 3, negative 1. The classical adjoint matrix, what it is it's going to be, and I'm going to write this as the adjoint of A. Sometimes this, by the way, is also called the adjugate matrix. Adjugate. It's supposed to be a T. But what this is it's going to be, you're going to find all of the cofactors, C11, C12, C13, and C21, C22, oops, C23, and C31, C32, C33. So that's going to be your matrix of the cofactors. You take the transpose of that, and that's going to get you what's called the classical adjoint matrix. So this is going to be C11, C21, C31, C12, C22, C32, and C13, C23, C33. Okay, so that's called the classical adjoint. Let's do an example. Let's look at this matrix A that we had. In fact, let's copy down our example. In fact, let's just reorder our, let's reorder everything here. Okay, a little housekeeping. All right, so in general, that's the definition of the classical adjoint. And so if we do an example with this matrix, what we have to do is we have to find the 9 cofactors. And so C11, what that's going to be is, remember, that's going to be negative 1 to the 1 plus 1 times the determinant of the corresponding submatrix. So in our case, that's going to be 1 times negative 1 is negative 1 minus 12, so negative 13. And so this is negative 1 squared, so negative 13. We're going to do this all the way down. So C21, C31, C21, C22, C23, C31, C32, C33. All right, and then I'm going to do this together with you. So let's see, C21. What we're going to get is we're going to have a negative 1. We might as well just put the signs in. We know how the signs are going to work. Plus, 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 minus, and the rest of them. And then we're going to multiply by the determinants of the 2 by 2 submatrix that we get by deleting the ith row, jth column. So C21 is going to be, if we delete the, let's see, where are we? Need to be a little bit careful here. I wrote these in a funny order here. Why did I do that? This should be C. I'm already getting myself in trouble. Mixing up, taking the transpose and mixing up the rows and columns can, I was really fighting muscle memory filling out this table. I don't know if you could tell. But this should be C12, C13. And then that'll give us the matrix of all the cofactors, and then we'll take the transpose to get the adjoint. And then at the end of the video, we'll talk about what's the purpose of this? What's the classical adjoint tell us? And it turns out it is actually useful. C12, we're going to get by looking at the cofactor. So we're going to get rid of the first row, second column, and that's 0, 4, 1, negative 1. And that's going to be, the determinant of that will be negative 4. C13, we're going to have 0, 1, 1, 3, so that determinant will be negative 1. C21, so now we're going to get rid of the second row, first column, So we're going to get 3 minus 6. So that's negative 3. So altogether that's 3. C22, we're going to have 1 times negative 1 minus 2. So that's, again, negative 3. C23, so we're going to have 1, negative 3, 1, 3. So it's going to be 3 minus a negative 3, or 6. So altogether that'll be negative 6. And then C31, the determinant will be negative 12 minus 2 is negative 14. C32, we're going to get 4 minus 0. So that'll be 4. So altogether negative 4. And then finally C33, we're going to have 1 minus 0, so 1. Okay. And so now we're almost there. So the adjoint, the classical adjoint, is going to be the transpose of the matrix that's negative 13, 4, negative 1, 3, negative 3, negative 6, negative 14, negative 4, and 1. And so the adjoint is going to be the transpose of that. So we're going to get negative 13, 3, negative 14, 4, negative 3, negative 4, and then negative 1, negative 6, 1. Okay, so that's the adjoint, the classical adjoint. Okay, so that's the classical adjoint of this matrix A. Now, why would we want to do that? I think that's a reasonably fair question. It turns out, and again, this is not something that I'm going to justify, but it turns out that if you take A times the adjoint of A, what you're going to get is you're going to get the, so if you take A times the classical adjoint of A, what you're going to get is the determinant of A times the n by n identity. So in other words, if you take A times the special matrix, you're going to end up with a diagonal matrix whose values are the determinant of A at each term in the main diagonal. In other words, if you want to find A inverse, so if you want to find A inverse, let's multiply both sides on the left by A inverse. So A inverse times A times the classical adjoint of A is equal to A inverse times the determinant of A, and then multiplying by the identity keeps it that way. And then this gets rid of the A inverse on the left. Well, so this tells you that the adjoint of A is equal to 1 over the determinant of A, I'm sorry, is equal to the determinant of A times A inverse. And this is really just another way to say that A inverse is 1 over the determinant of A times this classical adjoint. Okay, this is a super nice formula. If you have any programming background at all, I hope you can appreciate that telling a computer how to find the inverse using this formula is way nicer than having a computer find the inverse using anything else. So this is a really nice computational formula. It doesn't really give us anything new. We could have already found the inverse previously, but this is a much nicer way and therefore a much easier way to program. So that makes it much more useful to find the inverse of a matrix using any sort of computer technology. I just want to actually revisit one last thing. We know that for a 2 by 2 matrix, let's just say that this is a generic 2 by 2 ABCD. We know how to find of course, the determinant of A, but also the inverse of A. A inverse was 1 over the determinant of A times the special matrix. It turned out what the special matrix is it's the matrix of cofactors. And so the cofactors are going to be, so if you remember what happened, it was DA, negative C, negative B. You switch, so you have these signs that are negative because of the sign chart. So when you find cofactors, it should make sense that the off-diagonal terms there are going to be negative. They're switched because you take the transpose, and then each of the cofactors are just going to be the missing term. So for example, the cofactor, if you were to look at the cofactor C11, C12, C21, C22, in this case, C11 would just be what's the determinant of the 1 by 1 matrix that you get by deleting the first row, first column of A? Well, it's just D. And C12 likewise will be C, except it's really negative C, because you have the, so the minor is C and then the cofactor is negative C. Likewise, C21 is negative B, C22 is, you get rid of the second row, second column, you get A, you multiply by negative 1 squared, that's still A, and there you go. So there's the D, negative C, negative B, A that came about. That's really just all following from understanding the classical adjoint in general, understanding the cofactors and the minors, and then putting everything together. So this gives you a nice formula for the inverse of a matrix A. This formula, just very importantly, works for matrices of all sizes. So I think seeing it for a 2 by 2 can be helpful to kind of put it in context, but really it's going to be useful for when you have larger matrices.